Ionizing radiation. This lecture is going to cover what ionizing radiation is, and some of its properties and some of its health effects, how we measure it, how we protect against it. But before we begin, it's important to know that all ionizing radiation has one thing in common: the ability to produce ion pairs. And we'll talk about what ion pairs are in just a couple of minutes. The other thing is there are differences in various types of ionizing radiation. And these can be differentiated by how much penetrating power each type of ionizing radiation has and the level of ion pair production that may occur. There are two major types of ionizing radiation. One is a wave type, and the second is a particulate type. Now, the wave type of ionizing radiation can be thought of by looking at this electromagnetic spectrum. The electromagnetic spectrum starts down with very long wavelengths such as radio waves, AM/FM waves, microwaves, then gets into eventually the infrared range, and this is where a lot of your remote controls work for your televisions and those type of various systems, into the visible light range. Beyond the visible light range, you get into ultraviolet. Now, when you get into the ultraviolet range, the wavelengths are starting to get short enough to have quite a bit of energy. Some of this energy is enough to give you a sunburn if you're outdoors for extended periods of time without any sunscreen on. And as you get into the very short wavelengths of the ultraviolet range, you see here this little band that separates ultraviolet and X-rays. And this is where ultraviolet has enough energy to actually start creating ion pairs. So a portion of the ultraviolet spectrum can create ion pairs and therefore is classified as ionizing radiation. Beyond that, to the left, where the wavelengths get very, very short, you have your X-rays and your gamma rays, and these are areas where ionizing radiation is prevalent and the ability to produce ion pairs can occur. Anything to the left of this line here, which is just on the outside of the ultraviolet spectrum, anything over to the left is considered non-ionizing radiation. Now, there are health effects of non-ionizing radiation. I do not cover them in this class, but we will not be discussing those in this particular lecture. We'll be talking about only things that occur to the right of this band on ultraviolet. This is an atom. Just as a quick review, if you look at an atom, it has some protons and neutrons in the nucleus. The number of protons in the nucleus is referred to as the atomic number. The number of protons plus neutrons in the nucleus is referred to as the atomic weight or the atomic mass. With this particular atom, this atom has 3 protons in the nucleus, so it has an atomic number of 3, and 3 neutrons in the nucleus, so the total atomic weight or atomic mass is 3 protons plus 3 neutrons equals 6. Also note that it has 3 electrons. So this atom does not have any charge, it's stable and neutral. You have 3 electrons and 3 protons, so you do not have a charge on it. Now, this is an atom where ion pair production has occurred. And by ion pair, what I mean is that some kind of an energy, like wave energy from the electromagnetic spectrum to the far right, or particulate ionizing radiation with sufficient energy, can hit that atom and knock out an electron. Now, when an electron is knocked out of that orbital, what you're left behind with is a plus charge and a minus charge. This is considered to be an ion pair. Now, this looks pretty simple, and it actually is pretty simple. But one of the things I want to emphasize, as we'll get into later when we talk about some specifics on this particular process, is that this very simple process of creating ion pairs is responsible for all of the different effects of ionizing radiation that you can think of. And if you think of what ionizing radiation can do and why you may be worried about being exposed to it, some of the things that you think about are, well, it can cause cancer. Yes, it can. And if you look into mechanistically why it can cause cancer, it can cause cancer because of this process of ion pair production. Ion pair production is really, really important because processes that are involved in supporting your life, the biochemical and physiological mechanisms that are constantly occurring, require that the basic building blocks are working well. If an ion pair production occurs, for example, in a critical site like DNA, that DNA is not going to replicate properly because it's been damaged by the production of the ion pair. And improper DNA replication can also lead to cancer. Other health effects of ionizing radiation, from sunburns to cataracts, all can be attributed to this ion pair production. And some of the effects of acute ionizing radiation poisoning, where you start to lose blood cells, red blood cells, white blood cells, platelets, etc., where you slough off your GI tract, etc. Again, these are all due to ion pair production. And another aspect of ion pair production is that ion pairs can occur in almost anything that can be, this energy can come into contact with in your body. Most of your body's water. If sufficient ionizing radiation hits water, it can break it apart and produce very, very dangerous biological reactants, such as the hydroxyl radical, hydrogen peroxide. There's various secondary products, many of these things that are called free radicals. All of these can do biological harm because they contain unpaired electrons. And again, my point is that this process of ionization and ion pair production can be very dangerous in biological systems. And this is just another view of what can occur with ionization. In this case, you see that an atom has been hit by sufficient energy, and in this case of ionizing a particulate radiation, it creates an ion pair where an electron is knocked off, leaving behind a positive charge. So you now have an atom with a net positive charge. There are various types of ionizing radiation. For example, you have X-ray emissions, and you have emissions from radionucleotides, such as gamma, alpha, and beta. X-ray emissions are produced from man-made sources, usually where you have some type of a metal that is exposed to electrical energy, and when that occurs, the electrons in the metal will drop back to their ground state, and in so doing will emit energy in the form of X-rays. Or you can have emissions from unstable radionucleotides, which are trying to become stable eventually, and in so doing release energy. And some of this energy that they release is in the form of gamma waves, or alpha particles, or beta particles. And we'll discuss what each of those are in detail. X-rays occur when a photon is emitted from an electrical orbit, and it falls back to its lower energy orbit. When an X-ray emission occurs, it doesn't have a charge. Its speed is the speed of light, which I have referred to as c. X-rays have a lot of power, therefore they typically have kilovolts of power and range, but it could be unlimited. It could be as powerful as whatever instrumentation is devising the X-ray. And the range is very lengthy. It could be kilometers in air or meters in the body, meaning it could essentially go through you. Fortunately, X-rays have limited ion pair production, and what that means is that they generally hit at a pinpoint target within the body. I like to think of this as a BB. As we get into discussing other types of ionizing radiation, this is a small one. It's powerful, but it punches a very small hole through its target, and we'll call that a BB. Now, what happens when you produce ionizing radiation? Here I have a typical type of atom that has a lot of electrons in the outer orbitals. And when these electrons are hit with a lot of energy from electrical source, they will go out into higher energy orbitals. Once the electrical source is turned off, they drop back into the ground state. And when they do that, they release energy. And the energy that they can release is in the form of X-rays. So, for example, if you're going into your doctor's office and he's wanting to give you an X-ray, he might have something like this X-ray gun down here, where they'll be putting a lot of power into it, and it's going through typically a metal generally that has a lot of outer electrons that will be excited. And as these electrons are being excited, they go into a higher energy orbital, and once the source of power is gone, they'll drop back to their lower energy orbital and release that energy in the form of an X-ray, which we see coming off of here. Now, this process of hitting nuclear targets with excess energy and have electrons go up to higher orbital states and then drop back to lower orbital states is not unique. It's done with a lot of different systems that release energy, not quite as powerful as X-rays. For example, glow-in-the-dark toys. Some of you have played with glow-in-the-dark toys. When you play with a glow-in-the-dark toy, what you're doing is you're exciting electrons with visible light. And you saw where that was in the electromagnetic spectrum a little bit earlier, just between infrared light and ultraviolet light. So these are wavelengths that contain energy. It's being absorbed by the molecular constituents. What's occurring is that the electron orbitals are being excited. The electrons are going out to a higher energy state. You shut off the light, and that energy has to go somewhere, so it's going to be released. And it will typically be released in the form of visible light, but at a lower energy, i.e., longer wavelength than it absorbs. So these things tend to be sort of a greenish glow, because what's occurring is that energy is being released in the form of light. Alternatively, you can go to another part of the spectrum and look at microwaves. What happens when you are microwaving something? Well, let's say you take a cup of coffee and put in some, take some coffee, put it in a mug, put it in the microwave, and zap it for 30 seconds. Take it out. The mug is cool to the touch, but the water inside is very hot. Why? Well, what it's doing is exciting the electrons in water, specifically water. It's between the OH bonds. They are subject to a horizontal vibrational energy absorption. And when that occurs, they're absorbing wavelengths, discrete wavelengths in the microwave range to excite those electrons in that particular hydrogen-oxygen bond. Once the microwave is turned off, it releases that energy in the form of heat. And the heat is going to be good to warm up your coffee. And unless whatever in the microwave contains a hydrogen-oxygen bond, as in water, it's not going to be affected. So your coffee cup and any other thing that you put on your food, it will not heat up. Only things that contain water are going to be heated by microwaves. And it's the same principle here with X-rays. You're shining in, are exposing some type of usually a metal nucleus that has a lot of outer orbital electrons to some type of an energy source. They're being bounced out to a higher energy state. Once that source is turned off, the electrons go back to their ground state and they release energy in the form of an X-ray. And this will happen in the doctor's office, where they can quickly get an X-ray of your teeth or a broken bone or whatever part of your body that they're X-raying. Another way that radiation is created, ionizing radiation is created, is by the disintegrations of radionucleotides. Now, radionucleotides are atoms that are unstable. And what will occur with radioisotopes that are unstable is that they'll eventually try to get to a stable ground state. And they do this by successive types of release of different various ionizing radiation, such as gamma waves, beta particles, or alpha particles. I mentioned what atomic number was earlier. Again, atomic number is the number of protons in the nucleus. And I mentioned what atomic weight is earlier. An atomic weight is the number of protons plus neutrons in the nucleus. And this is important because the atomic number and atomic weight will change after a beta and alpha emission. And one of the things that I'll expect you to be able to do in this course is calculate how the atomic number and atomic weight will change following a beta emission or an alpha emission from the nucleus, as well as a gamma emission. And we'll also be discussing how to do half-life decay equations. So there are some equations that we'll need to do as part of this course, and I'll be going over those on the board for those of you that are in class. And this kind of summarizes what occurs with a radioactive atom. You have a nucleus that's trying to get to a stable energy state, and it can do this by the release of wave energy, which is, when it's a nuclear emission, is called a gamma wave, or particulate radiation, which for the most part, or at least what I'll be covering in this course, is alpha particles and beta particles. This is an example of a radioisotope going to its ground state. Now, I'm not going to test you on the specifics of this particular radioisotope decay chain. I'm just wanting to use this as an example of what occurs when uranium-238 starts up here in your upper right-hand corner and goes to the stable radioisotope lead-210. And when that occurs, you'll see that there are a series of steps that are going to be occurring where either a beta particle, an alpha particle, or a gamma wave are emitted from the nucleus, and that will change the atom that's left behind. Some of the ones that can be noted here, you have radium, going radium-226 down to radon-222. Radon is a particularly dangerous radioisotope because radon is a gas, and so if you have radon inside of your house, you can breathe it in, and this is part of a normal terrestrial type of ionizing radiation. you will find uranium-238 naturally in the environment, and these decay products are going to be occurring. And when they occur with radon present, radon is in the gaseous form, and it's an alpha emitter, so it can be particularly dangerous. But ultimately, this series goes down to lead. Now, a couple of things that I want you to be able to do with this. And one is I want you to know how to do some equations to describe, if you start off with a certain amount of a radioisotope, and you know what the half-life of that radioisotope is, how much is going to be left after so many half-lives have elapsed, or how much time has elapsed. And I like to use this equation here, A sub t equals A sub n times 1/2 to the n. And what that tells you is the amount that you're going to have at any particular time, represented by A sub t, is equal to the amount that you started with, which is A sub 0, times 1/2 to the n power. And n is the number of half-lives, and a half-life is a particular amount of time. And I'm going to go back to this in just a second, but the way this equation works, and this is something I'll be writing on the board for those of you that are in class, is if you start off with a certain amount of a radioisotope, you got here n sub 0, and you have a half-life of, let's make it a time. It says t sub 1/2 here, but let's say a month. And let's say we start with 100 microcuries. Well, after 1 month, going from this part here, time 0, out to time t1/2, which is in this case 1 month, we've gone from 50, and we've gone from 100, and after 100, how much is left after one half-life passed? Half of that, which is 50. Now let's go out in time another half-life. How much of that is going to be left after one more month, or another half-life has elapsed? And the answer is half of that again. So you go from 100, divide by 2 to 50, divide by 2 to 25. And you can continue to do this every time you reach another half-life. And this is important because what we're doing here, by the application of this equation, A sub t equals A sub 0 times 1/2 to the n, is dividing by 2. So these decay equations are actually pretty easy to do if you know how to divide by 2. All you need to do is determine how many half-lives are in the amount of time that's elapsed and divide by 2. And again, we're going to be working over some of those equations in class. We'll also be looking at some of the problems on decay constants. I do expect you to be able to convert from the decay constant to the half-life. I'll give you a half-life and want you to know what the decay constant is, and that's going to be this particular equation here. Decay constant mu is equal to 0.693 divided by the half-life. And know a little bit about the series decay and the radon daughters, some things that occur with those. Now, gamma emissions, what gamma emissions are is one of the radioisotope decay series. A gamma emission is indistinguishable from an X-ray, except that it originates in the nucleus. It, like an X-ray, is a photon. It's a wave, just on that electromagnetic spectrum I showed you earlier. Therefore, it has no mass and no charge. And whenever a gamma emission occurs, because it has no mass and no charge, there is no change in the atomic number or the atomic mass that occurs following a gamma emission. So, following a gamma emission, if you start with an atomic number of X, the atomic number will be X after the gamma emission. It does not change. Same with the atomic mass. If you start with an atomic mass of Y, the atomic mass will still be Y after a gamma emission. There is no change. And this is a gamma emission that's occurring. This is the next type of particulate radiation is beta. And I wanted to talk a little bit about a beta emission. These are also known as isobaric transitions. With the beta emission, what is occurring is a high-speed electron is being ejected from the nucleus. Now, because it is an electron, it has a charge. And because it's an electron, it has mass. So it's bigger than what you would see with a photon. And I like to think of this as the baseball in terms of the comparison. We've gone from an X-ray of a BB, now we're up to a baseball with the beta emission. And because it has some mass, it doesn't go quite as far as an X-ray. It maybe goes 30 feet in the air. It can penetrate tissue a few centimeters, and it's able to produce about 50 to 100 ion pairs in air, or 6 to 8 ion pairs in tissue, which is what we consider to be light damage. Again, this is the what I like to call the baseball. Now, what happens to the atomic number and the atomic mass following a beta transition? Well, with the beta particle, you've got a high-speed electron being ejected from the nucleus. and it's being ejected from a proton being formed from a change in a neutron. So what's occurring is a neutron is kicking off a charge, and the charge is a high-speed beta electron that's being emitted in the form of ionizing radiation. What's left behind is a neutron that has been changed by losing a minus one charge, so it now has a plus one charge. So when you look at what's occurring in the nucleus following a beta emission, what occurs in the nucleus is that a neutron is being changed into a proton. So, for example, if you start with 6 protons and 6 neutrons in the nucleus, and you have a beta emission, what occurs is that one of those neutrons is going to be changed into a proton. So, the following a beta emission of something with, well, let's use this example of 6 protons. Let's go to the example of 6 protons in the nucleus and 7 neutrons in the nucleus. Is that what I want?